Afternoon, everybody. Is this? Yes, it is. Good afternoon. I'd like to make a start because we are running really quite late now. I'm not going to make a huge introduction because I don't think, well, I want to move things as quickly as possible. I'd like to introduce Vijay, who's going to talk to us about, well, you'll find out in a minute. So welcome to Vijay, and it's 15 minutes per piece speaker. So thank you.
Any shorter, 15 minutes is fine. Okay, we'll see.
As short as you can.
Got it. Okay. Right. Hi everyone. I noticed in the previous ones, Alison, people when we were changing slides said change slide, please. Do I just use this computer at the front myself? Yeah. Okay. Great. Yeah. So yeah. Hi everyone. So I'm going to be talking about teaching the Laplacian and the wave equation to basically GCSE level and A-level standard, and then also experiences in first and second year undergraduate physics. So I'm Vijay Timms. I'm a member of the Institute of Physics. I don't normally put my letters after my name on talks like this, but it's pertinent this time because I finally joined the Institute of Physics after about 12 years of having it on my to-do list. So I finally joined a couple of months ago, finally got there. So I'm happy to be a member now. And when I became a member, I thought, well, I'll try and be an active member and get as involved as I can. So when I saw that the AGM was coming up, I thought, great, I'll come along to that. And when I saw that they were having this event and there was a call for speakers, I said, great, I pitched something to Alison and said, hopefully this will fit in. And she said, yes, that'll be great. So here I am. I'll just give some background, which will be pertinent to what I'm saying. So I graduated with an MSci in physics from Bristol University in 1998, where I was at one point taught by the esteemed Professor Vincent Smith, who's right there. Hello, Vincent. Thank you very much for teaching me second year nuclear physics. That was great. I then mainly did school teaching from 98 to 2002. Then I did a PhD in geophysics at the University of Liverpool, starting in about 2002, finishing in 2006 and graduating a year later. And then carried on doing university teaching work in geophysics in the geology department, which is pertinent because if you're a physicist in a geology department, you tend to be one of the people who knows much more mathematics than anyone else, and you're often a go-to person for other people because people, they often don't have an A-level in mathematics, and certainly normally don't have university level training, and they do come across mathematics involving things like the Laplacian and the wave equation in papers that they're reading, where they sometimes need some assistance in following what's happening. Interestingly, with the geophysics program at Liverpool, we'd accept people onto the course who had an A level in maths and physics of any variety, so grades A through to E, which was very different from when I was an undergraduate at Bristol, where I think the entry requirement then was 2 Bs in maths and physics, and at Imperial, where I am now, where we only accept straight A students. So there was a much more sharp disparity in the level of ability at mathematics when I taught this geophysics course and was on the program for 7 years than there is now, and has been at other times in my life. It was during this time because on the geophysics program, people did have to, it was hardwired into the syllabus that people needed to know how gravity worked and how electromagnetism worked and how wave mechanics worked. And so the mathematics was hardwired into the syllabus. And this meant that if we were teaching someone who wasn't so happy with mathematics, it meant that it was difficult for me to go into the nitty-gritty of the mathematics straight away. And I developed ways of helping students develop conceptual understanding of how certain aspects of vector calculus like divergence and curl and the Laplacian worked. And I think that's definitely been something that's influenced the way I do outreach teaching ever since. In 2009, I moved to Imperial College, where I've been ever since, back to a physics department. And so I've been a teaching fellow there ever since, where I know Ryan's here, who's also in Imperial. And I was very pleased. I think Melissa's gone now, but I know Gareth, who's there from Imperial as well. And I was very pleased to sort of see Melissa Uchida here earlier on. who I know from her earlier days at Imperial. So on the call for speakers, there were a few points, and one of the points was how do we present these concepts, outreach context in school and university. So I'm just going to do two things now. One is look at outreach in schools for the Laplacian and wave mechanics and how it's been taught there, and then I'll talk about in university, particularly years 1 and 2, when we teach core physics there. Okay. If anything's not clear when I'm talking, by the way, then please do shout out and just ask me to clarify. Okay. So talking to outreach groups of people where people in the outreach groups are people that might potentially do physics at university. One thing I always do from the almost at any age, bearing in mind that, you know, I don't do primary school outreach so much, but certainly secondary school and certainly when they're heading towards GCSEs, I'll always emphasize how important calculus is in physics, how important it is to know that. And indeed, it's essential to know calculus to actually take a physics degree. So if I'm doing outreach where the aim is to enthuse and inspire people about physics and get them to do it at degree level, you want them to do it for A level, and you also want them to be doing maths A level, or apology, I'm using A level for A level and equivalent in all of this dialogue, by the way. You don't need to mention the word or even the equations, but I believe that getting across ideas of things like the Laplacian and other aspects of vector calculus are possible and even fun to do, even at a high school level, so GCSE and A-level level. And it's also possible, a nice one, to get across the idea of a mathematical operator. That's something which is quite nice to do. To just demonstrate this, I'll just do a short slide where I'm going to show you some screenshots of various outreachy things that I've done over the years and how I'm able to get the idea of calculus and then lead on to ideas of vector calculus and even things like the Laplacian and wave mechanics into even GCSE level. It does depend on how much time you've got, of course, but even if I do a 20-minute snapshot talk, I'll even put in something to do with this. So on the top left there, you can see from a GCSE open day, I'd say if you want to be a physicist, then there are 3 important things. You need to be curious, you need to be doing experiments. You know, well, I don't necessarily mean tabletop experiments. I do clarifiers on what I mean by that. And know calculus. If you want to make it as a physicist, you need to know calculus. Not many people will know what that is. If you look at this top middle slide, I'll say why calculus. And what I'll do if I've got a bit of time, I'll ask pupils to, regardless of the age, I'll say, right, could you all try and define physics? And this can be a really fun activity. I say, could you define physics without Googling it, either on their own or in pairs or in a group? It's very fun to see what they come up with. So if you've got if you've got students in a room for like an afternoon of outreach, that can be a really fun activity to pick through the various answers. I then provide them with, you know, it's not my original definition, but it's one dictionary definition, not necessarily the best definition. You know, it depends on what you're using your definition for, really. But one definition which is nice is it's a science that studies the nature of matter and energy and how they interact and change in space and time. So science, good, I hope we'll all agree. Matter and energy, yes, interact and change in space and time. And I say, okay, if they change in space and time, you know, what does that mean? It means you've got things where if people know a little bit of calculus by that stage, if it's A level, I'll say, well, how's that manifested in equations? Well, it's d by dx and d by dt. Therefore, you can see from the definition that calculus is hardwired into what we need to do. If on the bottom left, I've got something from a 6th form open day where you can see I sort of say, right, for the core aspects of physics, you need to know about 5 areas. Classical mechanics, special relativity, thermodynamics, then the bottom 2, electromagnetism and quantum mechanics. I then show them the equations, which has aspects of vector calculus in there. The bottom one, you can see it's our friend, the Schrödinger equation, which clearly has the Laplacian involved, second derivative with respect to space. And if I've got time, I'll show aspects of the Maxwell equations and give a conceptual overview of what they mean and what the elements of the equation mean. Again, it depends on how much time you've got, but I like to do this even when you've got a snapshot. And this really helps develop students' enthusiasm for the topic before they've got to the nitty-gritty of addressing the mathematics. I'll not go on to this bit on the widening participation program. That's just that's just showing a snapshot of a syllabus when I've had 2 weeks to work with students, where I've basically made sure that that scalar and vector fields and how the mathematics works on that is included. This is not my slide. This is something from back in the days when I was doing geophysics outreach, which shows these hard black profiles show what's called a gravity anomaly. So the variation in the gravitational field strength when you go over an object which is relatively less dense than the rest of the surrounding ground. Okay, so the gravity dips a little bit. That tells you a little bit of information. Geophysicists, I don't know if anyone in the audience is a geophysicist, but geophysicists will look at the second derivative of this with respect to space, and that actually gives a more clear signature to eyeball on the nature of the gravity anomaly you've got under the ground. This relates to Gauss's law for gravity in 2D. So you don't bring in the equations in detail, but you do take them through this, and then as a sort of final slide, you can say this is how this is addressed in equation format, and you'll meet this in year 2 of your geophysics degree. So it's a very nice thing to do, is to get across how important these equations are, and then pinpoint if you learn how to do this properly when you get to years 1 or 2 of your physics or your geophysics degree. Okay, so that's the outreach part. I'll then move on to, oh, Alison, I can see people taking snapshots. So we're going to be able to share slides after this, after the tour. Yeah, so slides will be shared. So yeah, great. Yeah, so that's outreach stuff. Now on to university level things where I've taught both the Laplacian and wave mechanics. And I'm going to show you one where it hasn't worked so well, then something which was a bit better, and then something which is better still. So I've been at Imperial for many years now. I was once, for 5 years, I taught a partial differential equations course to year 2 students, where I essentially came along and did a cameo where it wasn't tied in with any other aspects of the student's degree. So I taught stuff which I love teaching. I love the mathematics of it. So these things are the classic problems they'd be doing. So top left, you've got a steady state plate. So they're essentially solving del squared U equals 0. Top right, they've got an iron bar where it's 0 to 100 degrees, and then you suddenly dip the hot end in cold water. And so that's essentially solving del squared U equals something proportional to the rate of change with time. Then you've got a plucked string. You pluck the string, that's del squared U is proportional to the second derivative with respect to time. And then there's the Schrodinger equation there on the bottom left. And so I was teaching pretty standard techniques in partial differential equations, separation of variables, this kind of thing, to get this across. The students didn't like it. They didn't get engaged. They were learning for the exam, and I could understand why. It's because it wasn't linking into any other aspects of the course. The parts they liked were when I brought in stuff which wasn't on the curriculum, when I said, this is how this works in real life. This is how I'd use it in geophysics teaching. But it wasn't, but it was a very difficult experience for me and the students to get them enthused when we were going through. Another experience I had worked better. This was when I actually taught second year electromagnetism. So I like that photo. That was used for the abstract for this. That actually happens to be from the electromagnetism lectures that I was teaching at the time, messing on with a Van de Graaff generator, where I was mainly teaching stuff to do with Gauss's law as the central theme. And I did a tag team with the vector calculus lecturer. In a sense, this worked brilliantly. The vector calculus lecturer, Marina Galland, would be teaching at 9 a.m. and me at 10, and we used to talk to each other to make sure she'd covered what I was going to use. And sometimes she'd teach something at night in the 9 a.m. class, and then I'd use it in the 10 a.m. class, which in a sense is the perfect way of doing things, and in another sense is not very good at all, because the students really need some time to be able to digest the mathematics before they can understand how it's used in the physics. So that worked nicely, but some of the students liked it and some of the students weren't so fond. Okay. In 2019, we did a wholesale curriculum review across Imperial College. I understand this was something that happened across higher education on more or less the same time scale. This involved consultation with various stakeholders, so staff, students, alumni, accrediting bodies. In the case of our department, this would be the Institute of Physics was the sole accrediting body, and others. Gareth will remember this wasn't entirely uncontentious, the way we reviewed the curriculum, but we got there in the end and we've come up with a much better curriculum than we had in the beginning. On the right-hand side, I'm just showing one aspect of the exercise we did to get people's involvement. We got all lecturers who taught courses, so this is year 2 differential equations, to write down all of the learning outcomes and then do their own assessments on roughly splitting it into thirds. This third is the most important part, this third is the second most important part, and this is the least important, and then green, green, yellow and grey accordingly. But we also printed these out on A0 posters and took them up to a common room and had a coffee and donut session where we invited all staff and all students to come round with post-it notes and say which bits they thought were most important and why, including alumni. And this was hard work, but it was an extremely rewarding exercise in seeing what people believed was the most important parts of the curriculum. What we've ended up with is something where we've now got modules that combine the mathematics and the physics in a way which for me, in all my years of teaching, works better than ever before. We now run modules with the mathematics and the physics much more thoroughly integrated. So for example, at Imperial now in physics, students do in year 1 a module, it's called Vibrations and Waves. It doesn't have a particularly dynamic or revealing title, but it includes the complex numbers course, a course on ordinary differential equations, the main course on waves, the basics of Fourier, a bit on electronics, mainly building up to LCR circuits and oscillations in LCR circuits, and then a bit of optics as well. And these are consolidated with what we 2-hour-long, what we call seminars, done in a modernized lecture theatre. This is Blackett Lecture Theatre 2 that we've got at Imperial College, where we've got these pods of 4 or 5 where students come and sit in the pods and they work on exercises with a module lead, and these are always exercises that try and integrate the maths and the physics, and they have a very light or zero assessment load, which means that students feel very safe to carry out the work when they go along. Okay. All right, that's all from me. I hope that's been useful and interesting for people, and I'll look forward to hearing comments. I think we're going to do comments at the end after everyone's spoken. So, all right, so thank you very much, everyone. Cheers. I'll computer.
The next speaker I'd like to introduce is John, who's going to come and talk to us on the next topic. So I just have to find out how to. Okay, so to go. Thank you.
Okay, thanks for that interesting start as well. And so yeah, onto this topic. So my background, so I'm a climate physicist. I originally did my PhD superconductivity, quantum mechanics at Lancaster, and one of the key things I think is important for this modern topic of climate is pulling information from other areas of physics into how we solve the climate system as well. And there is room for improvement as well. And just some pictures here as well. So that's a nice picture from where we live in Devon. It's got the ocean, the land, the moon as well. And all those aspects of the climate system are important to model it as well. So yeah, a bit louder. Speak a bit, I'll just speak a bit. Is that better? I wrote further, yeah. So I was just saying, so the top right picture, so you have the Earth, the ocean and the atmosphere and the moon, including all those aspects in how we model the climate system is essential. The ocean actually is as a boundary to the atmosphere, and it's often poorly resolved, that interaction. And the issue that we face when trying to understand the uncertainty is that they are internal waves created, which aren't always well resolved, unless we model that properly. So part of this talk will be showing that. That's an acorn I threw into our local river, a nice slow motion splash, and the waves rippling out. And the other picture here is taken from the web. That was the Tonga explosion down in the South Pacific back in February. And that was one of the first volcanic eruptions which has been so well monitored as well. You can just see the wave fronts rippling out from that as well. And the reason I've included that is come here on the next slide here as well. So yeah, stochasticity is part of the climate system. So uncertainty, intrinsic uncertainty is part of the issue. And the problems we're facing, the Earth's warming up because of anthropogenic fossil fuel burning. There's a climate sensitivity measure at about 2.3 degrees in the range, which is a very large range. The range divided by the point estimate is about 70%. It's not very well resolved. And as physicists, we've got an opportunity to make that better. The data to see this, you can see it's got radiative forcing and the global temperature anomaly. Then there's these blips down as well. Those blips down are when there's a big volcanic eruption, and that includes the amount of heat coming into the Earth, reflects away the sun's heat. Now they occur effectively randomly, almost like with a Poisson process, and that's a stochastic element. And this bit of research I published with Peter a couple of years ago, we are identifying there is a stochastic oscillator aspect as part of the Earth system, and that helps to reduce the uncertainty in the type of system that is resolved. That the lower picture, that's the group's resolution of that wave going around the Earth, just quite phenomenal, bouncing back and forth. And it wasn't big in terms of climates, but everyone experienced this as well. And this is the pressure gauge on the roof at Exeter University as well. And the first blip up is when the wavefront arrived. So it was a gravity wave going upwards, more density. And then it reflected over Nigeria and came back again. And you get the downward wave, came off the antipode back again. So everyone can see this, so they looked at it. Quite extraordinary. Let's come back to some of the challenges we have and what we can do about it. Can we best resolve the stochastic physics components? And there's room to improve that. System mechanics is a key part of what we learn as physics, partition function, entropy, and things. We can draw on things like random matrix theories, which were used both in nuclear physics in the 1940s and also in condensed matter physics in the 1970s and 80s to solve things like Anderson localization and electrical reduction problems. So that's something we're applying into climate physics to help better understand that. You can also use some of the maths of stochasticity as well. And there's some example of looking at extremes of population dynamics. And more importantly, we can apply this to how the current computer models are run for the climate system and evaluate that. The usefulness of these representations and that animation is like an Ising model or a percolation ones. There are certain universal features which we use to calibrate electron physics, nuclear physics. We can apply that also by principle into the climate system. And some of the challenges, yes, these animations are working. It was mentioned by the last speaker as well. So Hamiltonians are pretty much how wave mechanics is often resolved. Hamiltonian is potential energy plus kinetic energy, P plus V, and the Lagrangian is the difference between the two. But for a crystal system, you can partition space and time really easily. So the analytical solutions fall out and you get K wave numbers and you get energy oscillations. We get phonon vibrations as a result of that, so you get a whole raft of condensed matter physics from that. With climate physics, the issue you have is we have wave breaking and waves absorption. Energy across different energy scales needs to be included in new interactions. So we can't separate space and time, which makes it tractably very intractable. So in some sense, both the Hamiltonian wave mechanics formulation and the Lagrangian, the energy difference, are both important for this. And I mean, the rate of change of time, one will give you the cumulative energy changes, one will give you the energy difference change. almost orthogonal functions. So this is a picture of the rain fields on the tropics, which just goes to show the space and time aspects are hard to unentangle. And yeah, just to keep this short, because this is aimed to promote and provoke some debate as well. So climate system, it's resolved very coarsely. Part of the issue and things that we can do, the opportunity we have is to, can we better improve how well we know where the physics and the mechanisms are influencing and where they're not, what is truly random and what is explainable stochastic mechanics. Because there's a 70% resolution issue at the moment, there's room to improve that. That work helped to show we can reduce it by a factor 4, but we really need like a factor of 10 or 20 to get it really into the realm of operational physics solutions. Both the Lagrangian and Hamiltonian methods are really useful. Hamiltonian is super for wave mechanics and universality, but doesn't separate the wave function. So there's current research on that. And non-Hermitian mechanics, those in condensed matter physics, is looking at that, or fluid mechanics things. More system mechanics aspects are useful. And 2 extra notes I put from just the conversations that we've had here is, I mean, this is an urgent situation, the climate as well. And the skills we have in our communities would mean that scoping capability, your mainstream sort of career may be in one direction, but maybe there's roles to have, I like to spend 2 years working on a climate problem, a climate engineering secondment or a climate physics secondment, 2 years. Bring your experience into that field, because there's not the same breadth of theorists and engineering practitioners in climate physics as there is in solid state physics or nuclear physics. So all of us here could probably do a secondment there and it will help. And the other thing was about quantum computing. That's come up as well. And the algorithmic complexity is maybe it's a bit of a finicky detail. Let's just get it working as well. Where I'd say no. One thing that is really important is understanding the interaction between atmospheric dynamics and ocean dynamics. They scale in a non-linear way. And there's current rush to go from 100 kilometer scale atmospheric models to 1 kilometer really fast. Okay, oh, brilliant. And the capability for that might be quantum computing. But you'd need to start to resolve, rather than centimeter level ocean models, millimeter or micron level ocean models to make sure you don't mismatch boundary conditions. Otherwise, you'll create all sorts of internal reflections in the system, and that's going to amplify the uncertainty propagation rather than solve it. So knowledge of those boundary condition issues, PDE solving, these basic mathematics, Dirichlet boundary conditions or fixed boundary conditions, the standard one, need to be integrated into the design of the algorithms used of the climate users for quantum computers. So these include that, where you can influence as well. So that's my 2 bits there. So thank you.
Let's introduce Peter, who's going to give our next talk.
Thank you, Alison.
Help? Wrong one. Be a real challenge to talk to that. Thank you. Good, that's the hard bit. I'm Peter Waitman. I'm a physicist from the University of Liverpool, and I'm very pleased to have this opportunity to tell you about how we're translating our research in cancer into clinic. Now, someone in this audience quite likely has a lesion like this in their mouth. And the question they want an answer to is, will it become cancer? Because a histopathologist can tell you you've got cancer, but they can't tell you you're going to get cancer. And that is the big question that we're addressing. And of course, we're using the Laplacian and we're using wave equations. It took me a while to think whether we really were doing this, but we are because we're designing scientific instruments. The patients don't care. What they want is an answer to the question. Now, this oral cancer disease is rising rapidly. There are 12,000 new cases a year in the UK and 4,000 deaths. And 1 in 8 of these lesions becomes cancer, and it is a particularly horrible cancer. The question is to decide which do you have? And the histopathologist cannot help you because their best chance of predicting whether your lesion will become cancerous is usually less than 40%, which is worse than tossing a coin. And the problem with not knowing is that if you're the 7/8 of the people who aren't going to get cancer, you have regular yearly unpleasant biopsies. And for the people who are going to get cancer, the biopsies delay necessary surgery. So there's both over-treatment and under-treatment. And the person who told me about this problem was my colleague, Richard Shaw, who's a surgeon. And I said, well, you know, given enough money and several years, I think we could solve this problem. Whereupon he said, well, I'm seeing patients next week, Peter, and this doesn't half concentrate your mind. Well, it took longer and it cost more, but we think we've solved this problem. And we're using machine learning. We're looking at infrared spectral images of cancer because infrared spectroscopy is sensitive to the molecules that drive cancer. And infrared spectroscopy has been applied to cancer for several decades, but it's never made it into clinic. And the reason it's never made it into clinic is that if you look at one-dimensional spectral profiles from different regions of the tissue, you can hardly ever tell a difference. The secret is to extract the information that is there by producing an algorithm to assess a much larger data set. And you create the larger data set by dividing all these images in all possible combinations. And this gives you 10 to the 11 data points, which is enough to train an algorithm. Now, our first successes was on a simpler problem, which was esophageal cancer. And we were able to distinguish between cells that were not cancerous, but were which 1 centimeter apart in the esophagus of a patient, some of which were going to become cancerous and some of which were not. And the importance of this was that it would tell the clinician that this person's cancer is going to spread and this person's cancer is not going to spread. Now, the dream is to connect these infrared biomarkers to genetics. And then we can search for the underlying drivers that are common to all cancers. And the clinicians tell you this is absolute nonsense. But you have to have a dream. And we are making a little bit of progress in relating our infrared biomarkers to the genetics of uveal melanoma, eye cancers. Now, what comes out of an algorithm is a number. Does this convince a histopathologist? And in this case, it does. Our algorithm predicted one ratio, which gave sensitivities and specificities of the order of 99%. And on the left, you see a histopathologist's stained image. And on the right, you show the ratio image predicted by the algorithm. And it's pretty clear that it gives the same answer. The problem is both images are diffraction limited, and the infrared wavelengths are longer than the optical wavelengths. So the spatial resolution isn't as good on the image on the right, but the image on the right comes from 2000 wavelengths sensitive to chemical structure, whereas the image on the left comes from only 2 wavelengths. So if we can solve the spatial resolution problem, we can give a lot more information to the histologist. But can we solve Richard Shaw's problem? Well, this is what our algorithm gives us. It reduces the failure rate of 60% to less than 20%. Now, you do not recommend taking someone's tongue out on the basis of one algorithm. So we applied a second algorithm, and to our great relief, we came to the same answer. So this means we can now design an instrument to use in a pathology laboratory, which will greatly improve the accuracy of deciding whether a lesion will progress to cancer. But can we do better than this? Can we make an instrument that the surgeon can use in the operating theatre to interrogate a lesion and make the decision to operate without waking the patient up and taking a biopsy? So that is what we're now working on. And the approach is to use the technique that we developed to give more information to the histopathologist. Remember, the problem with our technique is diffraction limiting the spatial resolution. But if you work in the near field, you aren't limited spatially. And you can get spatial resolution equivalent to that of the histopathologist, if not better. And the pictures on the right show that we can provide the histopathologist with information on the chemical structure of the tumor. But more importantly, this technique can be used to make a diagnostic probe. On the right, you see a diagram of the Liverpool Diagnostic Infrared Wand, the elder wand. And what it does is it uses 2 or 3 wavelengths which have been identified from the machine learning algorithm as discriminating. And because you have only 2 or 3 monochromatic sources, you can make a very simple handheld instrument that is robust and cheap. And if you compare this with standard attempts to use Fourier transform imaging, they require a wideband source, they require a spectrometer, it's delicate, it's expensive, it needs maintenance, and you're looking at one-dimensional spectral profiles where you're not sure what it is you're looking for. And I'm pleased to say we're now funded to develop a prototype of the elder wand and have got a lot of interest from 2 or 3 companies. Now I'll finish by acknowledging the team that has done this, in particular, Barnaby Ellis and Connor Whiteley, who've just got their PhDs, and both of whom are working for companies doing machine learning. Richard Shaw, who gave us the problem, James Ingham and Paul Harrison, who are developing the electronics, Steve Barrett, who is an imaging expert, Caroline Smith, who manages our specimens, and Michelle Sigel-King, who did some of the original work on the Daresbury free electron laser. Thank you very much. And do put your tongue out in the mirror every morning.
Thank you very much, Peter. The next speaker is John.
Change it here.
Hi, good afternoon. My name's John Blackledge, and I'll tell you.
This is being recorded, so if you could stand
Oh,
by.
right, okay. I like to move around, but I've got to put a straitjacket on, then so be it. John Blackledge, who started a degree in physics in October 1977 at Imperial College, where VJ is. Okay, so good on. Now, at the time, the undergraduate admissions tutor became my personal tutor for a group of 3 of us. His name was Herbert John Payne, and he'd just written a book called The Physics of Waves and Vibrations. It's Wiley. It's still in various forms. I think it's still available. Maybe VJ knows whether it's still used as a book now, all these years later. Anyway, John Payne was an ex-RAF pilot, and he was very gregarious, and he was also chuckling to himself And he didn't always make things clear, but he was very enthusiastic. And I remember specifically him saying, you should buy my book, Physics of Waves and Vibrations. But remember, when you grow up, you'll realize that physics is waves and vibrations. And it took me about 45 years to realize what he was saying and that he was absolutely right. And I'm telling you that story just to introduce myself and to emphasize the remit of Allison's idea. The Laplacian, D'Alembertian operator, waves and vibrations is physics. So what I want to do is to give you a little introduction, as simple as possible, to something everyone should know, but they don't seem to. And I want to introduce Einstein's evolution equation and just in this slide say, where does it come from? What does it do? 1905, we all know Einstein published special relativity. He also did some excellent work on photoelectric effect. But one of his other papers, which is not quite as well respected as it should be, is a work on Brownian motion. It was the first time when he introduced this equation in the red box and using ideas which are purely based on random motion of ball bearings, if you like, little particles, and showed that from that equation, you can derive something that everyone knew, the diffusion equation. And therefore was showing that atomic theory really is real. It's a pity that you know, others didn't realize at that time, but this was long before atomic theory became reality. So this is one of the first papers of its type using statistical physics, as we call it, which was saying, yes, atoms do really exist. And the equation is here. This is, I got it off the internet. And there are some mistakes in it. First of all, and it's probably typing mistakes, because printing things was more difficult there. There's no time variation in the density function, which used f here. This is actually a correlation integral, when it should be a convolution integral. And secondly, do you see m here? It should be minus infinity. But mistakes aside, that is the basic equation. Now, in Einstein's work, what he did is he took a first order Taylor series in time on the left-hand side, and he took a second order Taylor series in space in the correlation integral on the right-hand side. He assumed that the probability density function phi was symmetric, and out pops a diffusion equation. And then he started to argue about the idea of random motion, atoms, and so on. So my aim on presentation show how this equation can be used to derive some basic field equations in wave mechanics involving the Laplacian operator, and then to take it a little further than that. So contents, evolution equation 3D, quickly introduce that. Kolmogorov-Feller equation, which is the same equation but introduces memory functions, a derivation of equations for wave mechanics. And I could stop at that point within the context of this SIP, but I want to push it a little further to introduce you to the fractional Laplacian and wave mechanics and fractional quantum mechanics, which is going to be a dominating theme in physics for many decades to come. And I'll leave you on that point. So what do we got here? This is in 3D. We've got the spatial vector, the usual stuff. You all know this notation. U is the density function. It's the number of these blue particles per unit volume undergoing a random walk. The red molecules are basically described by, the red balls described by the source function that's causing the random motion to occur. The probability density function, if it's a small density function, the range of this blue ball will be small. If it's a wide probability function, then the random walks will be quite large and it'll move a long way in a short period of time. This little cartwheel sign is a convolution operator, and I'd like you to note one of the most important theorems in physical equations, the convolution equation. Convolution real space is a product in Fourier space, so you can use that. So what does that help us do? Well, we can rewrite that equation as a so-called Kolmogorov-Feller equation. Kolmogorov and Feller, who did a lot of work in probability and nonlinear dynamics and so on. The basic idea, they took Einstein's idea and they said, look, instead of doing just a first order Taylor series, let's write it out as an infinite series. And then you've got a problem. There's no point having equations with an infinite series on one side. So what they did is say, right, let's write this lot here in terms of a so-called memory function, in the knowledge that if m is a delta function, it's equivalent to a first order Taylor series where tau is much less than 1. That's simple, it's a trick, it's an idea. Instead of having all these terms. So therefore, we can write Einstein's equation in 3D, where we have to define the probability density function and the memory function. And if we define those, we can then solve for the density function mu, given a source function, and see whether we get solutions which are useful. All right, one quick rough and ready thing. Suppose we let the probability density function P be a delta function. So delta function with that's minus u plus u, that term goes, and you're left with this simple. What's happened? No, all right, not my fault. You're left with this simple time-dependent equation if you just integrate up all this space. Memory function of this type gives you a solution for u of t, which is statistically self-defined. So the probability density of u over, as you get smaller and smaller, is the same at larger and larger scales. That simple equation, which has just come by shoving in a particular memory function and PDF, is the basis for things like the fractal market hypothesis, which is useful to economists, and also with work I've been doing over the last 2 years on COVID-19 pandemic data. So you see how Einstein's equation, with a bit of trickery from Mr. Kolmogorov and Professor Feller, and you can do things like that, ever so simple, by just defining different functions. All right, what's all this got to do with the Laplacian? Well, it's another trick. Look at the characteristic function for a Gaussian behavior and just approximate it this way. Shove that into this term, which in Fourier space is this product, put that result in here, and then note what we all know as physicists, the Fourier transform with a gradient gives you the frequency multiplied by square root of -1. Square it, noting the difference in the thing, then out comes the Laplacian. And therefore, you can use these derivation, a simple derivation of the wave equation. In terms of the Kolmogorov-Feller equation, which is Einstein's equation with a memory function, the little trick, if you let it be the gradient of the delta function, you introduce that, you end up, what's going on here? Something strange. Looks as though you're going to have some editing work to do.
Oh, go a little bit down.
Yeah, yeah.
Stand a bit closer to the microphone.
Yeah.
Turn it so.
It's that one there. So I hope that doesn't happen again. With these derivations of the Kolmogorov-Feller equation, out comes your basic standard classical wave equation with the Delamerton operator. This one here, using Einstein notation, all the box thing, which is usual. But also, if you choose the memory function to be a delta function with Planck's constant, but where time is effectively imaginary time, then the diffusion equation changes from describing a messy thing to waves, quantum waves. So in terms of this Einstein's equation here, in its more elegant form, you relate Laplacian to wave mechanics through the evolution equation. So two fundamental type of operators for in wave mechanics, the classical wave equation and Schrodinger's equation. I've also got here reference to a little paper where I talk about nonlinear wave mechanics, including freak waves, but that's old hat. Right, at that point I could stop. Actually, Alison, maybe I should. How much time do I have?
4 minutes.
4 minutes, okay, quick one. Push this a bit further. Instead of doing boring things like a Gaussian probability distribution function, introduce a little gamma function where it can vary, which was done by Paul Levy back in the 1930s. And you can do the same trick, and this time using the fractional Laplacian representation by Hungarian mathematician Marcel Ries. You can generate equations which are effectively wave mechanics, but you see where the spatial variable is not just an ordinary fractional, not del squared, but a fractional differential. And fractional calculus and the equations of fractional calculus is exponentiating at the most enormous rate at the moment. So physicists who don't know about this should start to know about it. One thing you can do, for example, if it's over very large timescales, effectively time independent, this equation, which is the fractional Poisson equation, where the relationship between the Levy index and the fractal dimension, number between 2 and 3, you can then represent a two-dimensional fractal in terms of the solution to that equation. I put this frontispiece up. It's a book I wrote over 20 years ago with some postdocs of mine, and it was on fractals and images and all that sort of thing with academic press. Did quite well. Although we didn't know it at the time, effectively the entire book was about solving that equation, which they was computer scientists, I was a physicist. I wanted to quantify something without all the paraphernalia that certain other people who are experts in certain other subjects get involved in. I'll pass on this, is that you can see the slides here, fractional quantum mechanics. I've got a summary there, I'm running out of time. So I just want 2 minutes, Alison, on this thing, because I think you might find this interesting. You can write the 3-dimensional fractional diffusion equation in terms of the usual for this memory function, in terms of first derivative, and then the fractional Laplacian. And then clearly, if gamma goes to 2, you have the classical diffusion equation. If gamma equals 1, which is equivalent to a Cauchy distribution with longer, fatter tails than you have with the Gaussian, you have what is effectively the continuity equation. So you've got the continuity equation for all these random particles going in a direction because it's being driven by a pump through a hose, turn the pump off, and everything starts to diffuse again. One other thing which is interesting, it's all very well mathematicians saying, well, put that to 1, you get this, put that to 2, you get this, put it in between, you get something different and solve it. But there's a fundamental theorem which you're all aware of in statistical physics, the most important theorem in statistics, the equivalent in statistics of Pythagoras' theorem in geometry. It's called the central limit theorem. And it says, if you leave things long enough, then eventually things will become normal and they will be related by a normal distribution. So in general, systems where gamma equals 1 will tend to go to 2. And you can almost think of that in terms of politics, economics, and philosophy. That the continuity of one idea, which is like a Cauchy distribution, whether it's in physics or in economics or in politics or in philosophy, will tend to go to the diffusion of many ideas, which is a Gaussian distribution. In other words, the Wealth of Nations, written in the 18th century by Adam Smith, led to Karl Marx's criticism of it. And what have we seen in recent history? It's all gone back to what it was originally, and it will continue to do so. And that requires disruptive concepts and ideas to diffuse them into different cultures, different countries, and so on. And to get that to work requires education in physics, and more physics. And there's no one here who's going to disagree with me on that. If you want to know a little bit more about my thoughts on this, there's a presentation where I talk about vocational education or all that sort of thing. But physics is the key to it. One last thing I can say, if I just have a little bit of time, my first professorship, I was appointed to a head of the department of mathematics, and they all wanted to know what I was about. So I presented myself to them. I said, I'm very privileged to be head of a department which is, after all, the queen of all sciences, mathematics, the queen of all sciences. But just remember, physics is the king. Thanks for listening.
Martin is our final speaker.
I think I will not be brave enough to try and change this myself, as Simon can help. While Simon's coming to do that, let me say that I'm an astrophysicist from Glasgow University. And Jonathan may be interested to know, if you don't already, that next year is the 300th anniversary of Adam Smith's birth. And the following year is the 200th anniversary of Lord Kelvin's birth. So I, for one, will be looking at your thoughts on that in the video clip. I'm in the process of trying to persuade the university that we should make something of this, since both of them are Glasgow alumni, and exploring connections between their two worlds might be a very fruitful avenue to explore. But for today, I'm going to briefly explore the world of gravitational waves. I've said I'm an astrophysicist. I'm also a member of the LIGO scientific collaboration. I'm not here speaking on behalf of LIGO, nothing quite so grand, but I am the chair of the Education and Public Outreach Group and the Communications Division of the LIGO collaboration. So I'm mainly going to focus on the ways in which we've woven ideas about waves, the mathematics, the physics of them, the actual measurability of them into some of the public outreach we've done since the first detection occurred. I hope everyone is aware that we have detected gravitational waves. We're coming up on 7 years since the first event was detected, although it wasn't announced until the following February. Took us 5 months to be absolutely sure. What's happened since then, in just about 6 years since that first announcement, is that the number of confident detections we've accumulated has grown to be 90. So attention is switching in a lot of our public outreach, and indeed in a lot of our scientific activity, to what we can learn from populations of events rather than individual events. But we are seeking to ensure that we don't lose some of the key messages about what actually are these waves in the first place, rather than assuming that that's all just understood now, because these are, deeply counterintuitive ideas. So I've put together a few slides that just take some snapshots of things we do in relation to the 4 questions that Alison posed. So the first one, how do we present these concepts in the outreach context at school, university, to industry, and indeed to other researchers? So I'm mainly focusing on that as we go through the slides, but a few points will relate to 2, 3, and 4 as well in due course. So of course, the key idea to get across here is the notion of gravity not as a force, but as the curving of space and time. So let me echo what Vijay said. I think a very important concept, even for those that don't understand in quantitative detail calculus, is that physics is all about understanding changing phenomena. And of course, the complication in terms of solving the wave equations is that these are not waves traveling through space, but waves in the fabric of space and time themselves. So that brings all sorts of difficulties in setting up your coordinate system and solving the equations. Sadly, there isn't really time to go into that today. I mean, that deserves a talk in itself, but we don't get into the gory details of that in public outreach. We generally stick with what's largely an unsatisfactory analogy, but it served us quite well, which is the stretch rubber sheet analogy that I'm sure you've all seen countless times before. And yes, we know it's far from perfect because it begs questions like, well, what's space-time curving into and so on. So I think a topic I would be happy to explore with others in their applications of waves and wave dynamics is how we can improve on metaphors like that. But for now, let's stick with it and note that the key point here is that you get gravitational waves when that space-time curvature is changing. So again, even on a non-mathematical level, you're building in the idea that it's all about dynamic fields. So the other important concept, I think, is the fact that you can't generate these in the lab. So I'll come back to that in a minute. But just before I do, let me flash up before you some of the public outreach resources that we've put together for our main announcements of detected events. These are typically black holes colliding with the occasional neutron star thrown in for good measure. And as I say, much of our outreach resources focus on the properties of the sources. Everyone loves black holes, but we are very much still in the business of communicating and building up a deeper understanding of the actual waves themselves. So some of our more recent events have included black holes that have something to say about the process of how they evolve. And indeed, in recent years, there's been ways to connect a lot of that to things like the Event Horizon telescopes, amazing popularity of their images of the supermassive black holes at the center of our galaxy and neighboring galaxy. So what about at undergrad level or early postgrad level? Well, there probably aren't too many departments now that go for a sort of full-blown maths with tensors and singing and dancing treatment for undergrads, but we're still doing that in Glasgow at least. So in a few weeks' time, I will be embarking for yet another year on the challenge of presenting that to students who in their first degree or in the early years of a degree will not have had exposure to that kind of math. So again, what we've sought to do is to deliver the appropriate level of mathematical rigor, but really focus on the physics principles that maths supports, so that they emerge from having done our course in gravitational wave detection and general relativity, not just able to manipulate the algebra, but to have some deeper physical understanding of what it all means. Easier said than done, believe me. But again, the feedback has generally been quite good. But the sort of flagship maths result does at least bring in our Laplacian. But the key thing here is to emphasize a couple of points, which I'll say more about in the next few slides. One is the fact that that H there is a metric perturbation, and this is us looking at the situation of a wave that's been generated and is propagating through the universe, and we're trying to look for its effect on our patch of space-time. And these are going to be very small perturbations. The whole derivation is based on H being small, and they're also essentially the free space solutions. So that's about as far as we can push things with the undergrads or early postgrads. And the people within our collaboration that actually go on to solve the generation of the waves really require a great deal lower specialist training in order to get their heads around that. But if everyone doing our course has at least grasped that, what emerges from looking at the propagation of the waves is a wave equation, and moreover, a wave equation where the speed is the speed of light. So gravity travels at the same speed as light, then we're kind of happy that we've achieved our main goal there. So quickly moving on to the second, what's the significance of these concepts in different physics specialisms? What must be measured, modelled or represented? Well, the key thing I want to stress here is that, yes, we've got our cartoonish picture of the masses accelerating around each other. It's deficient in some respects, but the one thing it allows us to talk about is just how stiff that rubber sheet is. If we think of space-time as our rubber sheet analogy, then whether or not you include the explicit maths, you can talk about the coefficient that relates the thing we measure, which is the stretching and squeezing of space-time, the space-time strain, to what generates it, which is the quadrupole moment of the mass distribution. That coefficient, I mean, just look at it, G over C to the fourth. You can get, high school students to work out how small that number is. And let's face it, you don't really want two black holes colliding in your backyard. So if these are happening far away, then what we measure is further diluted by the 1 over D factor, the distance that the wave travels. So all of that, of course, means even if you're not going into that level of detail, it sort of makes sense of the public outreach story about just how incredibly faint these signals are. But what it offers, if you've got a bit more time, is to explain what the faintness of the signals tells us about the weakness of gravity in relation to the other interactions, and the fact that you can't produce these in the lab. You need to use the cosmos as your laboratory. So that leads us into how the detectors work. Well, today's not a talk about that, and I'm by no means an expert in that anyway, but there's a lot you can play with there that is going beyond how we calculate the waves to how we would be sure that we've measured something and how we can characterize the parameters of the source that's produced the waves. So a popular approach that we use a lot in public outreach, once we've set up the basics of it about, essentially using the lasers in LIGO and our fellow instruments Virgo and Cagra as incredibly precise measuring devices, is that those measurements can be swamped by local disturbances. So it's crucial to isolate the detectors as best you can from all of that. Or in other words, you want to basically keep the noise down. So the diagram like this that shows a variety of different sorts of noise that can swamp the signal we're after, the strain, 1 part in 10 to the minus 23 or thereabouts. A good metaphor for that seems to work quite well, and it's better than just a qualitative one, is to talk to high school children, or indeed primary children sometimes, about how noisy it might be in their school lunchroom. And if they're trying to hear a conversation of someone on the other side of the table, if there's a lot of background noise, it's mighty hard to do. But if they have a general idea of what that conversation is about, it's a whole lot easier. And we actually do some little practical exercises around this, where one group of kids gets to read out a secret message, Another group have to listen for that message, and the third group get to make as much noise as they can. You can guess which group like the task best, but what that's giving them some insight in is the real challenge we faced in getting to the point of announcing the first detection. It wasn't just about the technology advances, those were of course incredibly impressive, but it was also about understanding well enough what the signal should look like. And that involved solving wave equations, and it involved a lot of maths that there isn't time to go into today, but we try in our outreach to remind people that those theoretical leaps forward were just as important as the instrumental ones. And that's allowed us to also weave in aspects to do with data analysis, template matching, you know, again, using that analogy of the conversation in the lunchroom. If you think you know what the conversation is, in fact, the way we've played with that is to give the group who are listening to try and get the signal, we give them a library of phrases and tell them it's one of these guys, and it's amazing how well they do. Whereas if they don't have that prior information to go on, it's much, much harder. So that's an analogy for the task of turning predicted signals into parameters that, you know, of course, opens up a bunch of stuff to do with Bayesian inference and fields that are relevant far beyond the scope of just solving the wave equation. A couple of final remarks just to wrap up then. So what other awkward mathematical terms appear? Well, again, really this deserves a talk in itself, but I'm not an expert in this from within the collaboration. But what we have striven to do in our public outreach activities is to emphasize just how much harder it is to solve the equations in some cases which are not the simplest, not the vanilla ones where you've got equal mass black holes, no matter around. And in fact, nature's been kind because in the first few years, we've seen examples of this that can help us to illustrate those difficulties. So one of our events involved two black holes with very different masses, and that led to a much richer harmonic structure in the signal. And interestingly, a lot of newspapers picked that up because we could highlight the fact that those higher harmonics were like listening for rich structure in musical chords. So we had stuff about how one of our signals sounded just like Elvis's I can't help falling in love with you. Like, we didn't come up with that, the Daily Mail did, but you know, it certainly went down well in terms of explaining a difficult mathematical concept. The other big challenge in solving the equations is when there's matter around. So if you have neutron stars colliding, yes, the great thing is that it gives off an EM signal, but it's a lot harder to understand exactly what the combination of the gravitational wave signal and the EM signal is telling you, because stuff happens when the gravitational wave starts plowing in to this surrounding material around our pair of neutron stars, as indeed happened in August 2017, just over 5 years ago. So that's going to be a big field for the next few years, we very much hope, but it's going to require a lot of computational power to understand the way in which the gravitational waves and the surrounding matter interact. Almost done. How is this significant within the sector? Well, I hope I don't have to convince you too much of that. It has been a big news story in recent years. The detection of gravitational waves, indeed the IOB no less, listed it as a breakthrough of the year, not just in 2016, but in 2017. The way we like to emphasize this for a general audience is to make the point that for about 400 years, we've been restricted to the EM spectrum in terms of viewing the universe. In fact, for most of that 400 years, it was just the optical window. But gravitational waves are fundamentally taking us beyond that spectrum. And indeed, they're already helping us answer some pretty significant questions, like the prediction from the theory that gravity should travel at the speed of light is borne out by observation. Again, happy to discuss that more later. We're in the position of being able to do very high precision tests already on GR by looking and solving the wave equation both before the merger, during and after, and seeing if the different parts match up. And then the part that I'm most directly involved in is looking at the use of gravitational wave sources to constrain the expansion rate of the universe. Horribly looking complicated slide, but really the takeaway message is we're not there yet, because we've only thus far got a few dozen sources with which we can do this. But Next March is when our next observing run is set to begin, and that will be pushing us up to, we hope, several hundred detections within about a year to 18 months. And well, I think that means that we've got a pretty bright future, but I think the challenge for us is to continue to not just focus on what we use these waves for, but the waves themselves, because that's a story worth telling. That's what we've tried to do for the last 6 years. We're going to keep doing that. I think in some other areas of astronomy, we've almost lost that, because the product of what, say, a giant radio telescope observes is amazingly impressive. But telling the story of how we get that data is worth telling as well. The EHT, the Event Horizon Telescope, I think did that pretty well, because it was so revolutionary to combine data from all these different radio telescopes. So that was an important part of the story. We want the wave part to be an important part of our story as well, not just what it tells us. I better stop there. Hope I haven't overrun. Thank you.
Thank you for all 5 speakers. And I'm sorry, I'm being very fast because I want to save as much time as possible for discussion. There should be some afternoon tea outside. I'd like all of you to mill around with each other. Now, one of the thoughts I had was, do we actually want to come back in here because it's so hot? Would we prefer to spend the rest of the discussion time out in the other room? Could I have a show of hands for those who prefer to stay out there? Yeah, okay. So once you've got your cups of tea and you've had a chance to talk to people one-to-one, I'll pull us back together we'll stand in a circle out there and we'll have the discussion standing up, but in the cool. So please go and get yourself a cup of tea and so on, and I'll pull us back to order in about a quarter of an hour.
Yeah, sure. Yeah, sure.
Yes, I did a lot it went on through July.
Sure. Yeah, I'm an advocate of that because I don't like I'm generally quite an advocate of that kind of approach, especially for outreach, especially in school teaching. Yeah, if I was to teach that way,
Most of the graduations
I've already demonstrated that they might. I haven't big enough to do it. Mathematics to explain to them as well at the same time. But I'm very much